Imagine creating something today that will still be deadly 10,000 years from now. Not 10 years, not 100 years, 10,000. To put that into perspective, 10,000 years ago humans had just begun farming. The pyramids did not exist, written language did not exist, civilization as we know it had not even started. Yet right now, in our modern technological world, we produce a material that must remain isolated from the environment for longer than the entire span of recorded human history. I'm talking about high-level radioactive waste. And the question that naturally follows is this: how can something remain dangerous for that long? Let me explain. Inside nuclear reactors, atoms like uranium are split in a process called nuclear fission. This releases enormous energy, which is why nuclear power can generate electricity for millions of homes. But the process also produces radioactive byproducts, unstable atoms that release energy as radiation. Some of these isotopes decay quickly. For example, isotopes like cesium-137 and strontium-90 have half-lives of around 30 years, meaning their radioactivity decreases by half every 3 decades. But others are far more persistent. One of the most well-known is plutonium-239, a byproduct of nuclear fuel. Its half-life is about 24,000 years. Let me explain what that means with a simple analogy. Imagine you start with a barrel of radioactive material today. In 24,000 years, only half of it will have decayed. After another 24,000 years, half of the remaining half disappears. This process continues slowly for hundreds of thousands of years. In fact, scientists estimate that some nuclear waste must be isolated from the environment for 10,000 to 300,000 years, depending on the mixture of isotopes. So the real challenge isn't just creating nuclear energy. The real challenge is managing the legacy it leaves behind. Think about that for a moment. We are designing storage systems today that must remain stable through earthquakes, climate changes, political shifts, and possibly even the collapse of civilizations. And here's the truly fascinating part. This problem forces scientists, engineers, and governments to think on timescales almost no human system has ever dealt with before. Not decades, not centuries, but geological time. So in this video, I want to break this down clearly, almost like we're standing at a whiteboard together, and explain why radioactive waste lasts so long, what makes it dangerous, and how scientists are trying to solve a problem that stretches far beyond our lifetimes. Before we go deeper, let's map out the 6 key scientific insights that explain why radioactive waste remains dangerous for thousands of years and what scientists are actually doing about it. Think of this like a roadmap for the whiteboard. Each point reveals a different layer of the problem. Here are the 6 key ideas we're going to unpack. First, we need to understand what radioactivity actually is. Many people imagine radioactive material as some mysterious glowing substance, but in reality, it's simply unstable atoms releasing excess energy as they transform into more stable elements. Understanding this basic atomic behavior is the foundation for everything else. Second, we'll explore the concept of half-life, one of the most important ideas in nuclear physics. This is the reason radioactive waste can remain dangerous for tens of thousands of years. Half-life determines how slowly certain isotopes decay, and why some materials stay hazardous long after civilizations rise and fall. Third, we'll look at what actually makes nuclear waste dangerous to living organisms. Radiation itself is simply energy, but when that energy interacts with human cells, DNA, and tissues, it can disrupt biological systems in powerful ways. Understanding how radiation affects the body helps explain why containment is so important. Fourth, we'll examine where nuclear waste is currently stored. Most people assume there is some massive global facility managing all radioactive waste. In reality, a large portion of it is stored temporarily near the nuclear plants where it was produced, often in cooling pools or sealed dry casks. Fifth, we'll break down the concept of deep geological storage, the strategy scientists believe may safely isolate radioactive waste for tens of thousands of years. This involves burying waste deep underground in stable rock formations designed to remain undisturbed for geological timescales. And sixth, perhaps the most fascinating problem of all, we'll explore how future civilizations will even know these sites are dangerous. Because when you're dealing with 10,000 years, language may change, cultures may disappear, and warning symbols may lose their meaning. In other words, scientists aren't just solving an engineering problem, they're solving a communication problem across millennia. So in the next section, we'll start with the most fundamental question: what is radioactivity really, and why do atoms behave this way in the first place? Once you understand that simple principle, the entire mystery of nuclear waste suddenly becomes much clearer. Let's start at the very beginning. What is radioactivity, really? Here's what's really going on inside an atom. At the center, you have the nucleus made of protons and neutrons. Surrounding it are electrons, which form the cloud that defines chemical behavior. Normally, atoms are stable because the forces inside the nucleus are balanced. The protons repel each other electrically, but the strong nuclear force keeps them together. But some atoms, like uranium or plutonium, have too many protons or neutrons, or the ratio between them is off. Think of it like a stack of unevenly balanced coins. Eventually, the stack wants to tip. The atom does the same. It seeks stability by releasing excess energy in the form of radiation, particles or electromagnetic waves that escape the nucleus. This process is what we call radioactive decay. Let me explain this with a simple analogy. Imagine a leaking water tank. The tank is too full, and the water starts to leak slowly, drop by drop, until it reaches a stable level. Each drop is like a unit of energy, released by a radioactive atom. Some tanks leak fast isotopes like iodine-131 decay in days. Others leak almost imperceptibly. Isotopes like plutonium-239 will leak energy for tens of thousands of years. That's why some nuclear waste remains dangerous for such unbelievably long times. Now, why does this matter for humans and life on Earth? When radioactive particles escape and interact with living tissue, they disrupt the normal chemistry of cells, especially DNA. This is why radiation is dangerous. It can damage tissues, increase cancer risk, and even affect entire ecosystems if exposure is high enough. In other words, the energy from an atom is invisible, but the biological impact is very real. Here's the takeaway for your understanding. Not all radiation is the same, and not all isotopes behave the same. The danger lies in both the intensity and the longevity. A small dose of a short-lived isotope is very different from a tiny amount of a long-lived one, and that's exactly the challenge of high-level nuclear waste. Finally, even though this seems abstract, understanding it gives us a framework for solutions. Knowing that atoms are leaking energy helps explain why we need deep storage, shielding, and careful handling protocols, the engineering solutions that protect us for thousands of years. Now that we understand why atoms become radioactive, let's talk about half-life, the concept that determines just how long nuclear waste will stay dangerous. Half-life is a term you may have heard tossed around, but here's what it really means. It's the time it takes for half of a radioactive substance to decay. Not all of it disappears at once, only half. Then half of the remainder decays in the next period, and so on. Think of it like cutting a loaf of bread in half repeatedly. You start with a full loaf. After one cut, half remains. After the next cut, only a quarter remains. After the next, an eighth. This continues indefinitely. And although the amount keeps shrinking, it never truly reaches zero. That's why some radioactive isotopes remain dangerous for tens of thousands of years. Take plutonium-239, for example. Its half-life is about 24,000 years. That means if you started with 1 kilogram today, in 24,000 years, only half a kilogram remains radioactive. After another 24,000 years, only a quarter remains, and so on. The decay is slow but persistent, a trickle of energy that continues across civilizations and eras. What the research shows is that this is not just a theoretical problem. Scientists designing storage sites must account for geological changes, climate shifts, and even potential human interference, because the material will remain active far beyond our lifetimes. IAEA 2022. Here's a simple analogy. Imagine leaving a small campfire smoldering in a dense forest. At first, the smoke is heavy and obvious. Over time, it fades, but the embers remain hot for days, capable of reigniting. Half-life works like those embers. The energy is invisible but persistent, and even small remnants can be dangerous if exposure happens. Now, from a human health perspective, half-life determines how long we need to protect ourselves and the environment. Short-lived isotopes are easier to manage. They decay relatively quickly. But long-lived isotopes like plutonium-239 or iodine-129 require decades, centuries, or even millennia of isolation. Understanding half-life also gives us practical insight. It's not just about containment now, it's about planning for the far future. Engineers combine this knowledge with shielding, dry casks, and deep geological storage to minimize risk. Strategies we'll explore in later sections. Now that we understand what radioactivity is and why it lasts so long, let's explore why it's dangerous, not just in theory, but for living systems like your body. Here's what's really going on inside your body when radiation exposure occurs. Radiation is essentially energy released from unstable atoms. When it passes through tissue, it can ionize molecules, meaning it knocks electrons off atoms. This might sound abstract, but the biological effect is very real. Ionization can damage DNA, proteins, and cell membranes, triggering mutations, impaired cellular function, or even cell death. Let me explain this with a simple analogy. Imagine your DNA is like a blueprint for a house. Each cell in your body is a builder referencing this blueprint to maintain your structure. Radiation acts like tiny sparks landing on the blueprint. Some sparks do no major harm, but repeated hits or intense exposure can tear or smear the blueprint. The builders, your cells, now make mistakes. Some of these mistakes lead to malfunctioning cells, which can manifest as cancer or organ dysfunction over time. What the research shows is that even low doses of radiation, over extended periods, can have cumulative effects. This is why long-lived radioactive waste is particularly concerning. It's not about immediate explosions or fires, it's about prolonged exposure, slowly interacting with life forms and ecosystems. National Research Council, 2020. From a practical standpoint, containment strategies are designed with this biology in mind. Shielding materials, like thick concrete or lead, absorb radiation and prevent it from reaching living tissue. Deep geological storage isolates the material entirely, placing it in stable rock formations far below the surface, where human or environmental contact is extremely unlikely. Here's a behavioral takeaway. While we're not personally handling high-level nuclear waste, understanding this principle helps us apply root-cause thinking in our own health. Just as shielding and isolation prevent cellular damage from radiation, we can protect our bodies from chronic stressors like oxidative stress, poor diet, or environmental toxins through strategic lifestyle choices. Think of antioxidants, proper liver support, and circadian rhythm alignment as your biological shielding against invisible damage. Now that we understand why radioactive waste is dangerous, let's look at where it actually is and how it's stored. This is where the problem moves from theory into the real world. Most people assume there is some grand, centralized facility handling all nuclear waste. The truth is more complicated. Right now, a large portion of high-level radioactive waste is stored on-site at nuclear power plants, often in cooling pools or dry casks. Cooling pools are essentially massive water tanks that keep spent fuel rods submerged. The water acts as both a shield against radiation and a coolant to prevent overheating. Dry casks, on the other hand, are sealed metal or concrete containers that hold waste after it has cooled sufficiently. They are robust and engineered to last decades, but here's the key. These are temporary solutions, not permanent isolation. The waste inside can remain radioactive for thousands of years, far beyond the expected life of these storage structures. USNRC 2023. Let me give you an analogy. Think of a smoker storing cigarette ashes in a jar. The jar contains the immediate hazard. Smoke and flames are gone, but the toxic residues remain. Over time, if the jar leaks or cracks, the hazard spreads. Similarly, temporary storage facilities work in the short term, but they are not designed to last for millennia. Another challenge is that storage is often near populated areas, which raises both environmental and political risks. Earthquakes, floods, human error, or even intentional tampering can compromise containment. That's why long-term storage solutions must consider not just engineering, but societal stability over geological timescales. From a scientific perspective, the takeaway is that current storage is a stopgap, designed to keep waste safe until more permanent solutions like deep geological repositories are completed. But the clock is ticking. The isotopes inside these casks won't wait for human infrastructure to last. Here's a practical connection for you. This situation highlights a principle we often see in health and metabolism. Temporary fixes rarely solve root causes. Just as a cooling pool or dry cask cannot neutralize radioactive isotopes, simply masking symptoms like fatigue, weight gain, or hormonal imbalance doesn't fix the underlying metabolic dysfunction. True solutions require long-term foundational interventions, whether it's in energy management, liver health, or fat metabolism. Now we come to the most ambitious and long-term solution for radioactive waste: deep geological storage. This is where science, engineering, and long-term planning converge to tackle a problem that spans thousands of generations. The idea is deceptively simple. Instead of keeping waste near the surface, bury it deep underground in stable rock formations. These sites are chosen for their geological stability, areas unlikely to experience earthquakes, flooding, or volcanic activity. The goal is to create a natural barrier that, combined with engineered containment, will isolate radioactive material from the biosphere for tens of thousands of years. Here's what the research shows. Facilities like the proposed Yucca Mountain Repository in the US or the Onkalo Repository in Finland are designed with multiple layers of protection, engineered barriers like metal canisters and clay buffers, geological barriers provided by solid rock site selection based on long-term climate and seismic stability. Let me explain this with a simple analogy. Think of radioactive waste as a dangerous chemical you need to store safely. Instead of putting it in your kitchen cupboard, you lock it in a vault inside a reinforced concrete bunker, and then bury the whole bunker deep under a mountain. Even if humans forget it exists, nature itself helps keep it isolated. What makes this fascinating and incredibly challenging is the time scale. Plutonium-239 has a half-life of 24,000 years. That means engineers are designing facilities that must remain intact longer than most civilizations have existed. They must account for erosion, glaciation, and even possible human curiosity. This is not just an engineering problem, it's a lesson in thinking far beyond the human lifespan. From a practical perspective, there's a parallel in health and metabolism. Just as radioactive waste requires long-term layered protection, maintaining energy, weight, and longevity requires systems-level interventions, supporting liver function, managing insulin and cortisol, optimizing sleep, and providing your body with antioxidants and nutrients to buffer against long-term stress. Short-term fixes alone are never enough. Here's a natural call to action. Understanding this principle helps us appreciate why patience and long-term thinking matter, whether we're managing environmental hazards or our own health. If you're finding this approach insightful, subscribe. We dive into science every day, breaking down complex problems and showing practical, long-term solutions for your body and life. Now, let's dive into one of the most fascinating challenges of all. How do you warn future civilizations about radioactive waste when language, culture, and symbols may change completely over 10,000 years? Here's what's really going on. We can design the most stable, impenetrable storage facility on Earth, but if humans accidentally dig into it thousands of years from now, the consequences could be catastrophic. So scientists are not just engineers, they are also time travelers in thought, thinking about how to communicate danger across millennia. Let me explain this with an analogy. Imagine leaving a note for someone 10,000 years in the future. Would they understand the words, the symbols, or the meaning? Probably not. Even a simple warning like "danger, do not open" might be completely meaningless if the language has evolved or disappeared. To tackle this, scientists are exploring multi-layered communication strategies, universal symbols, sharp triangles, jagged lines, or intimidating shapes that naturally signal danger. Cultural storytelling, myths, stories, or monuments designed to encode the idea that a site is hazardous. Physical deterrence, massive spikes, jagged structures, or unappealing architecture meant to intuitively discourage curiosity. This is more than just creative thinking, it's a profound lesson in planning for uncertainty. High-level nuclear waste forces us to think on scales far beyond our lifetime, an exercise in humility and foresight. OECD NEA 2020. Here's a practical parallel for your life. Just like radioactive waste, the stressors and toxins in our bodies can have long-term consequences if we ignore them. Small, invisible damage accumulates over years. Oxidative stress, insulin resistance, or chronic inflammation can silently undermine health. The solution, like the scientists' approach to nuclear waste, is layered, forward-thinking strategies, consistent nutrition, liver support, sleep optimization, and metabolic balancing. Notice a theme emerging? Both in nuclear waste management and in health, we are solving problems not just for today, but for long-term stability. Quick fixes and short-term solutions are insufficient. Success requires understanding the root cause, building durable systems, and thinking ahead. As we wrap up, let's step back and connect the dots between radioactive waste, science, and practical lessons for our own health. We started by exploring why nuclear waste remains dangerous for 10,000 years. Unstable atoms release energy in the form of radiation, slowly decaying over millennia. The concept of half-life showed us why even tiny amounts can persist far beyond our lifetimes. We examined how radiation interacts with living organisms, disrupting DNA and cellular function, which underscores why careful containment is critical. We also looked at the realities of current storage, the temporary solutions like cooling pools and dry casks, and why these are not permanent fixes. Then we explored deep geological repositories, where science and engineering combine to protect the environment for tens of thousands of years. Finally, we tackled the fascinating challenge of communicating danger across civilizations, showing that planning for the long term is not just technical, it's deeply philosophical. Here's the key takeaway. Radioactive waste teaches us a powerful lesson about long-term thinking and root causes. Just as we cannot ignore the persistent hazards of nuclear isotopes, we cannot ignore the slow cumulative stressors in our own bodies. Metabolic imbalance, chronic inflammation, poor sleep, and nutrient deficiencies are invisible threats that compound over decades, just like radiation. The solutions require layered, sustainable strategies, supporting liver health, managing insulin, reducing oxidative stress, and optimizing lifestyle choices. So here's the challenge: try just one long-term intervention today. Maybe it's adjusting your meal timing to support metabolic balance, prioritizing restorative sleep, or adding liver-supporting foods like cruciferous vegetables. Track how your body responds over weeks and months. Small, consistent actions compound into resilience, just as careful storage today protects the environment for millennia. If this added value, like the video and subscribe to join others who are exploring science in a practical, life-changing way. Remember, understanding complex systems, whether nuclear waste or your metabolism, is not just intellectual, it's empowering, and it gives you the tools to take meaningful, actionable steps every single day. The next time you think about radioactive waste, I want you to also think about your own body. What are the invisible forces shaping your health, energy, and longevity? And how can you take action today to safeguard them?